x, y, and z. Okay? And it satisfies the following three conditions. Your I here is non-negative. It's an integer, non-negative. Okay? So it can be either 0 or 1, 2, 3, whatever. This string, this pumped string, also belongs to your language. So you take your string of this form, and so y is your substring that you're going to pump. Increase multiple copies of it here. Now remember, I is non-negative. So here's your string now pumped. So there are multiple copies of y get inserted in the pumped part, if you like. I copies of y, right? And y itself, the length of y is positive, can't be 0, right? And the third condition, it's put in more for convenience of proof, for proving things, but there is a third condition, not so essential, but that is that the length of x, y, so the first two parts of your three parts, right? You've got a three-part string, right? So the x, y part of it, its length is less or equal to p, right? So if those three conditions get satisfied, well, if A is a regular language and you've got this number p, then you can divide S this way. Okay? Now use. Do you understand the point of it? Now use modus tollens. If you cannot do this, if these conditions are not satisfied, then back to here. A is not. Then not A is a regular language. Right? So satisfying these conditions is a way to show that your language is regular. And if these conditions, just one of them, cannot be satisfied, then, well, your language A is not regular. So you've got yourself a means to detect whether a language is regular or not. A much more rigorous way than using intuition that can fail, like the two examples of languages C and D we did before. Right? Your intuition, your common sense can fail. So we need something more rigorous to detect a regular language from a non-regular language. Okay. Now a few comments. So that's the statement. A bit of a reminder here. The S with the vertical bars. That's just the symbol for length of the string S. It's defined as the length of the string. In other words, how many symbols does it have in the string? Okay. And Y to the I, that just means you concatenate I copies of Y. Okay. So just substring Y, 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 Y. Okay. I times. That's what this means. Right. Now Y to the 0 is just is epsilon, which is just the empty string. Okay. Now when you split your string S into X, Y, Z, and these three parts, three substrings, right? Now X and Z could be the empty string. And you can do that way, but Y is not allowed to be the empty string. Now that's condition 2 here, because the length is positive, right? Can't be 0. So therefore, your Y, the middle part, cannot be epsilon, cannot be the empty string. Now, why is this put here? Because without it, your theorem becomes trivially true. Becomes trivial. Do that as homework. Convince yourself that that's true. If you did not have this condition, then so you only have these, then the theorem becomes sort of trivial. Convince yourself of that as homework. Let's see. well, those are sort of obvious, right? Condition 3, that the length of the first two parts together, x, y, is less, has a length at most p. Right? It could be equal to p, but less than, at most p. And this is used for convenience in the mathematical proof. So we'll come back to this later when we get into the actual proof, right? Now, mentioned here in the exercises in the end of the chapter. So exercise 1.74, you actually use this condition in an application, in a problem solving 1.74. All right. Okay, so that's a bit of notes, comment on the theorem statement. Now we get to the actual proof idea. I don't know if you can see the second line here, maybe not. The proof involves partly something called, if you're a computer science guy, you may have heard of this before, something called the pigeonhole principle. So getting a bit ahead of myself, but giving you a feel for what's coming. All right. So the proof idea, so the overview of the proof. So you have some machine, and let it be a DFA, so deterministic finite automaton. Here's its formal description of your machine. Right? We've done that many times. Okay, and let's assume that this DFA recognizes the language A. Right? So that immediately you know that language A is regular. Okay, by definition, because what is a regular language? Well, it's a language that is recognized by a machine. Right? The DFA. Okay, so this language is regular. So we're assuming we have a regular language to start with. Okay. Now let the pumping length p be. Now this is just a positive integer. Okay, positive integer. Yeah, otherwise trivial. Okay, positive integer. So, so let the positive p, the pumping length, let that be equal to the number of states of this machine. Okay, so p equals the number of states. And I'm getting into the next session, but so we'll now show that any string in this regular language, okay, so any string in that language, string s, okay, that has length at least p. Right? In other words, its length is at least the number of states in the machine, n. Okay, so at least length p. That string s, that you can break it down into the three pieces x, y, z. Okay, that satisfy three conditions. So that's the essence of the proof. Okay, we'll prove that that's possible. So recapping a little bit, you've got a language A. You know it's regular because there's a DFA M, this machine, that recognizes it. Okay, so it's a regular language. We choose a pumping length P, just some positive integer, that's equal to the number of states in the machine. Okay, and then we will prove, right, that any string S in this language whose length, there's a condition, whose length is at least P. P is the pumping length, so the length of the string is greater or equal to that length P, where P is the number of states in the machine. Then that string S, you can break it into three pieces, x, y, z. Okay, and these pieces x, y, z satisfy the three conditions. That's the main direction of the proof. And then for the next session we start actually proving that can be done, that you can take that string, and break it into these three pieces XYZ, and that these three pieces XYZ satisfy the three conditions.